Hi everyone, we're going to get started with chapter 4b today. So the first topic in chapter 4b is calculating molarity using the moles of a solute. So let's go into molarity. This is a really important concept in chapter 4. So before working with molarity, let's define concentration. So this gets into this broader concept of solution stoichiometry. We're thinking about moles in solution. So the concentration of a solution is the amount of solute present in a given quantity of solvent or solution. So we know for a solution, it's composed of a solute and a solvent, typically water for a solvent, but we can see other kinds of solvents as well, and then different solutes dissolved in that solvent. So altogether, that makes up a solution. So now to describe a solution, we have molarity. So the molarity, this is really a really key concept here in chapter 4b. So the molarity is the moles of solute per liter of solution. So molarity, moles of solute per liters of solution. So our units here, if you see this capital M, you should instantly think moles per liter. So moles of solute per liter of solution. Again, this is a super important concept in chapter 4 and in general chemistry 1 in general. So to describe a solution, if we're asked to calculate the molarity, it's the moles of solute per liter of solution. So another way you might see this is that molarity can describe a concentration. So this is where these equations come in. So molarity can describe a concentration. It's still the number of moles per liter. Another way to see this is the number of moles, where N is denoting the number of moles. So that's lowercase n, number of moles. Then this volume term here is usually in units of liters. For a concentration, just generally concentration C, it doesn't necessarily specify that it's in a mole per liter. Molarity is always in moles per liter. So concentration, though, could be presented in millimoles per milliliter, micromoles per deciliter. So concentration is number of moles per unit volume. Then from there, we can rearrange this equation. So we can have concentration is equal to number of moles per unit volume. We can also then have the number of moles is equal to the concentration times the volume. Right, so we're rearranging this equation, multiplying both sides by the volume. So then number of moles N is equal to the concentration times the volume. So to show you these units worked out, if we have N as our number of moles, does it still make sense for these units? So concentration is moles per liter. Then we would be multiplying by a volume term, so liters. So this does lead to liters and liters canceling out. Then moles here are left. So we can rearrange this equation to also solve for the number of moles of our solute. So don't forget throughout all of this that N is the number of moles of solute, then the volume term is based on the entire volume of the whole solution that encompasses both the solute and the solvent. Then another way to rearrange this is we can have volume then is equal to the number of moles over the concentration. So volume is equal to number of moles over a concentration. Then that's really volume is equal to number of moles over the concentration is in moles per volume. When we have a fraction in the denominator, we can basically multiply the numerator by the reciprocal, so volume per mole. Then we are canceling out moles and moles to leave just units of volume, or just a volume term that can be in liters or milliliters, for example. So we can have all these different versions of the equation, this one, and this one. So that's all for just one solution. So these are the same variations here too. So with these different variations of the equations, let's see what kind of problems we can solve. One example of a problem we can solve is preparing the solution of a known concentration. So let's say we're in the lab and we want to make a concentration, a certain solution with a certain concentration. Well, we have moles per liter, but in the lab, we're not going to be able to measure out moles, right? So we want a number of moles, but we can't just go to the balance and measure out number of moles. So instead, we have to measure out a number of grams, then convert that into moles, or convert moles back into grams by use of our molar mass. Right, so we'll use the molar mass to connect grams to moles for the solution, and then we can measure the volume here. So to execute this, the first step would be to weigh out a certain number of grams of your sample. If you know the number of moles we need, we can convert that into grams by use of the molar mass. Then, once we have that solid in the bottom of a volumetric flask, for example, we're going to add a small amount of volume to start to get this solid dissolved. Then we will fill up the remainder of this till we hit this volume mark to make our overall solution. For example, though, if we had 20 molarity or 20 moles per liter, but if we only wanted to make, let's say this was 250 milliliters. Well, this is on a per liter basis, but 250 milliliters is really 0.250 liters, right? So we move that decimal point over 3 times to the left, or we divide by 1,000. So if we want a 20 mole per liter solution, but we only want 250 mils of it, or only 0.250 liters of it, then we would need to figure out how many moles do we need if we only end up needing a 250 mil solution, or 0.25 liter solution. So here we're basically taking 1 liter, but dividing it by 4. So if we had 20 moles per liter, we would also need to divide this number of moles by 4, right? So this would really be 5 moles needed per 250 mils, or 5 moles needed per 0.250 liters. Right, so these are still ratios that are the same. So we'll get more into this, but you don't always have to make a 1 liter solution. You can also make a 500 milliliter solution or 250 milliliter solution. You just have to adjust how many moles then that's equivalent to, because molarity is units of moles per 1 liter is how we end up reporting it. And again, we'll take the mass of some compound, convert it to moles, and then we'll have that volume. Then all of that comes together to give us a molarity, which we report in terms of moles of a solute per liter of solution. So the really important concept here is molarity and units of molarity and calculating molarity. So let's go into this practice problem. So we have a chemist prepares a solution of this ionic compound, and they want 11 micromoles of barium acetate into a 50 ml volumetric flask. So here's already, we don't have a full liter, but we do want to make a 50 ml solution, and we want this many moles. So we can solve this. We're going to need to convert micromoles into moles, but ultimately what we're asked for, actually we don't have to convert because we're asked for our final answer in terms of micromoles per liter. So to be clear, in a micromole per liter, this is definitely a concentration, but this is not technically a molarity, because units of molarity has to just be in terms of moles per liter and not micromoles per liter. So this is not really molarity. We could get there, we can convert this into molarity. Right now, this is just calculating a concentration in micromoles per liter. So not molarity, because molarity is moles per liter. So let's go on to calculate this. Before we do that, actually, let's figure out what we have. So we have 11 micromoles. Out of our concentration calculation, which is concentration is equal to N over V. What is this 11 micromoles? Which variable is that here? So N is our number of moles. So this is N, the number of moles. Here it's in micromoles, and that's fine. We can work with micromoles. Then we also have this value here of 50 milliliters. Is this our concentration? Is this our volume? So these are the only two remaining now, and that's our volume. This is capital V, this is a volume term. So with our volume, we will have to convert milliliters into liters, but for the number of moles, this is already in micromoles, and our answer asks for the final answer to be in micromoles per liter. So now we can plug these values in and do this unit conversion, and then we'll get our final answer. So let's do that now. So here's some review of what we talked about. The concentration of a solution is the amount of solute given in a volume of solution. Concentration is a more broader term, and it's kind of the umbrella term. If we were to describe, here's concentration, sort of an umbrella term, then molarity is a form of concentration, always reported though in moles per liter. Again, concentration could be in micromoles per liter, millimoles per deciliter, etc. So concentration is this broader umbrella term. Molarity is more specific. It's always moles per liter. So here in this practice problem, we're asked to give the concentration, not the molarity. So give the concentration in micromoles per liter. So now to calculate this, we know our equation we're going to use. We know the value for N. We know the value for the volume. Then we can plug in our values, and we'll do that on the next slide. And here's a reminder of what N and V and C stand for in this equation. So now on the next slide, we can start plugging in values into that equation. So concentration is N over V, our number of moles over a volume. We want to report this in ultimately micromoles per liter. So let's take our volume in 50 milliliters. To get this into liters, we need to have milliliters in the denominator to cancel this out. So there are 1,000 milliliters per 1 liter. Now we can cancel out mils and mils. 50 divided by 1,000 gives us units of liters, so that's 0.050 liters. So now we have the correct volume term in the units that we want. So concentration is equal to number of moles over volume. The number of moles we had in the practice problem, that's 11 micromoles. So this symbol, remember, means micro, going back to our chapter 1 unit conversions. So 11 micromoles divided by the correct volume unit now in liters, so 0.050 liters. Doing that division, we should get about 220 micromoles per liter. Here's some additional notes. So micromole, this is pronounced micromole because this symbol here is micro. And then something else you might see, so technically we've been listing out molarity in terms of moles per liter. We can also state this as micromoles per liter in terms of molarity is a micromolar. Okay, so for typical molarity, we know it's moles per liter. If we have micromoles per liter, so this part is still moles per liter, that's still molarity. So then to finish off this connection, we have this micro hanging out that is not accounted for in just stating molarity. So molarity again is moles per liter only and always. If it's micromolar or micromolarity, that means we have micro here in the numerator. So that's micromoles per liter. So to connect that here, we did calculate 220 micromoles per liter. To get this into scientific notation, we want just 2 sig figs. So technically, if we put this decimal point here, that's 3 sig figs, right? So we just want 2 sig figs. So to get this into 2 sig figs, we take the decimal point, so 220, move it over 2 times. So that's 2.2. We only want 2 sig figs, so 2.2 times 10. Move the decimal point over 2 times to the left. That's 2.2 times 10 to the second units of micromoles per liter. Then based on the connection we just made, where moles per liter is still molarity, and then we add in this micro out here, so this becomes micromolar. molarity. So now we have also the answer could be stated as 2.2 times 10 to the second micromolar. Again, we had to put it into scientific notation because we want only 2 sig figs. And again, 220 with a decimal there, that is 3 sig figs. So this would be wrong. So 2 sig figs, here's our final answer. Then for the next topic here in chapter 4b, we're still going to do more on molarity. So now we're going to kind of build in complexity here using molarity. So use molarity to now find the solute moles and solution volume. So before going through this practice problem, let's remind ourselves that concentration, the general term is moles per some volume. So some amount of moles per some volume, or even more broadly, the amount of solute per volume of solution. Here, though, in this practice problem, right away, let's notice that this capital M describes the concentration. This is no longer a general term for concentration. This is our molarity term. So always for molarity, it's always the number of moles of solute per liter of solution. So always just moles, not micromoles, always just liters, not milliliters, not deciliters, always just moles per liter. So right away when we see this capital M, I want you to get used to writing out, so 0.229 capital M or molar, but that is, what is that really equal to? 0.229 moles of solute per, now technically it's 1 liter of solution, and we usually don't write in this 1, but it can be helpful to visualize it that way. So 0.229 moles of solute per 1 liter of solution. So we know that from our capital M, this gives us a lot more information than just seeing that capital M. So I suggest breaking this down into what it is, so moles of solute per liter of solution. Then we also have this fact that the chemist added 30 mils of that solution. So our volume term right now, we could say 30.0 milliliters. So we have all this information. Then we're asked to calculate the millimoles now. So millimoles. So at the end, we want millimoles of potassium permanganate. So millimoles of our solute. Just a quick note on potassium permanganate, or this permanganate ion. So technically this does contain a metal, but I mentioned previously in chapter 4a that these polyatomic ions do not break down further in solution. So even though this contains a metal, this actually does not further break down. So it does not further dissociate. So even though it appears that it could be an ionic compound, this permanganate ion is sort of an unusual exception. So it contains a metal and a nonmetal, but it does not further dissociate in solution. So just something to be aware of, something I mentioned in chapter 4a that I wanted to clarify. So generally our polyatomic ions do not further dissociate in solution. Okay, so just something to note from what I mentioned previously, this does contain a metal, but this is a polyatomic ion. It does not further dissociate in solution. Okay, so now we're going to calculate the millimoles of our solute given the molarity and given this volume. So again, as mentioned, I would see this capital M and pretty much right away rewrite this to actually state in terms of the full units. So this is really 0.229 moles of solute. In this case, our solute is potassium permanganate. So our moles of solute dissolved in each 1 liter. So each 1 liter of solution. So capital M, we can rewrite it like that. Then for our practice problem, we want to solve for the number of moles. So that's what it tells us. To solve for the number of moles, we do have to convert that into millimoles if it's not in millimoles, but ultimately we want to find the number of moles. So to rearrange to solve for the number of moles, we would multiply both sides by the volume. This leaves concentration times volume is equal to N, the number of moles. So to solve for number of moles, we rearrange that equation. So now we're going to solve for N by taking the concentration times the volume. So we'll solve for the number of moles this way, then make sure we convert it into millimoles. For some additional context on rearranging this equation, so this is a formula for calculating the concentration from total moles of a solute and the volume of a solution. So we can solve for concentration that way. Another variation then is a formula for calculating the total number of moles here of a solute in a given volume. So let's say we have a given volume of a solution with a given concentration. So in this case, we could solve for N, the number of moles, which is what we're going to do in this example. Then yet another variation is a formula for calculating the volume of a solution with a given concentration that contains a given total moles of solute. That means we're asked to solve for volume, and we are given the concentration. We're also given the total number of moles of solute. So all these different variations to solve for either concentration, number of moles, or volume. So we'll get used to working with all these different variations of this concentration equation. One thing we should look at first is we have liters of solution. That's our molarity term, comes from our molarity term. But here we have 30.0 milliliters. So the first thing we could do is convert this into milliliters, so then these units will be equal. So let's go ahead and do that. So we'll take 30.0 milliliters, then the conversion between milliliters and liters. You can write it out like this. I like to picture it as 1,000 milliliters in a liter, but this is the same thing. So this is really saying 10 to the negative third liters in 1 milliliter. So whichever conversion factor you like to use. Again, I like to use 1,000 mils in a liter, or 1,000 grams in a kilogram, or 1,000 milligrams in a gram. So this goes back to being comfortable with these unit conversions from chapter 1. If you have any questions about this, definitely feel free to let me know, and we can work through some more practice problems together. So now we have 30.0 milliliters divided by 1,000. That does come out to 0.0300 liters. So 30 divided by 1,000, we still want 3 sig figs technically, so 0.0300, where this is a sig fig, same with this 0, and same for that 0. So remember, those are all sig figs. Now that we have our volume in liters, so going back to that equation, we're going to solve for moles. So that is a concentration times a volume. Now we have the concentration, we have the volume. Let's plug in those values now. So now our molarity was stated as 0.229 moles of solute per liter of solution. So 229 moles of solute per liter of solution. So that's our concentration term. Then for the volume, we have this term here of 0.0300 liters, so 0.0300 liters. If we didn't remember this form of the equation, we could also be sure that we're getting the right answer by having the right units cancel out. So here's liters canceling out with liters. And importantly, this number of liters here was described for the entire solution. So going back up to our practice problem, this is telling us that we have 30 milliliters of the whole solution. So it's not just saying we have 30 milliliters of some stock concentration. We just need to be reading this carefully to say 30.0 mils of solution. So now going back here, 30.0 mils of solution, we converted that into liters. Now liters of solution cancels out with liters of solution to then leave about 0.006870 moles of our solute. Then we're not quite done because that question specifically asked for this to be in millimoles. So now we're going to take 0.006870 moles, and we're keeping the full digit here, the full value, because we're not yet rounding. So we're not yet at the end. So I'm going to keep this full amount in your calculator. So take that entire answer, and then we're converting this into millimoles. So we have moles here in the numerator, then for every 1 mole, there are 1,000 millimoles. So this is the same thing essentially as taking 1,000 milliliters in 1 liter, but here we're changing out liters, right? So now we're changing it to moles and moles, but same concept. So that milli prefix is for every 1,000 milliliters, there's 1 liter, or for every 1,000 millimoles, there's 1 mole. So now we're taking this amount times 1,000, essentially moving the decimal point over 1, 2, 3. So then that's 6.8700 millimoles. Importantly, we read that question again to make sure it's millimoles. So here, report your answer in millimoles. So an important detail to catch, and now we need just 3 sig figs. So to get this into 3 sig figs, we just need 1, 2, 3. So then our final answer here is 6.87 millimoles of our solute. In this case, our solute is potassium permanganate. So then this 30 mils was given in the problem. Really, this is our answer here. So 6.87 millimoles. And we use that equation, we use this form of the equation. Now for the next topic in chapter 4b, we're still building on this concept of molarity. So using molarity to find the solute mass and solution volume. So let's look at this practice problem. So we have this much volume. We're given the moles per liter. This could have also been stated as 0.344 molar. So this is moles per liter, copper 2 sulfate in a solution, so aqueous copper 2 sulfate, right? So it's in a solution where the solvent is water. So whenever you see a solution, think about what's your solute, what's our solvent. So this is our solute, and then water is our solvent. So here we're going to calculate the mass in grams of our solute, and we're given this information to go based off of. So let's start labeling some things. So for the volume, we have 0.40 liters. This is of our whole solution. So some important detail, I like to write out as many details as we can. So this is 0.40 liters of the whole solution. Just to keep that in mind, it's describing the whole solution. Then we have this molarity here. This is 0.344 moles of solute per 1 liter of solution. So again, I like to take this molarity term and write it out. We could even substitute in this term here, so copper 2 sulfate, because that's our solute. So we have from this equation, number of moles over volume. We have a concentration here, right? That's our molarity. We have a volume. So now we can rearrange and solve for number of moles to be concentration times volume. So multiplying both sides of this equation by volume, number of moles is equal to concentration times volume. But after we get number of moles, in this question we're asked about the mass. So ultimately we want the mass in grams, and if we have number of moles after doing this equation, how do we go between moles and grams? So we need to make use of our molar mass of copper sulfate, or copper 2 sulfate, I should say. Okay, this has to be copper 2 sulfate because Cu2 plus and SO4 2 minus. So copper 2 sulfate, we can get grams of copper 2 sulfate using the molar mass. So let's start to plug in these values here, and then we'll end up solving for grams. Here's some additional context to essentially what I was mentioning. So this 0.344 moles per liter, that's really 0.344 moles of copper 2 sulfate dissolved in each liter of solution. We want to solve for the number of moles, then go into grams. To also know this, we were given a concentration and given a volume, but we don't have N here, so that's our only unknown. So let's solve for N. So to plug this in, we have N is equal to concentration times volume. Our concentration given in the problem is 0.344 moles of solute per 1 liter of solution. So here's our concentration. Then for our volume term, it was given as 0.40 liters. So then at this point, to cancel out, also I can specify this is liters of solution. So now we can cancel out liters of solution, liters of solution. We do this multiplication step here to just get our units of moles per, or moles of solute. So the moles of solute comes out to 0.1376 moles of solute. All right, so here's our volume given. Here is our molarity. So we plug those values in. We have this many moles of solute. The thing to go between number of moles and into grams is by use of that molar mass. We need to calculate the molar mass of copper 2 sulfate. So we would do that by looking at CuSO4. We need the mass of just copper, 1 sulfur, and then 4 oxygen atoms. When we add all that up, we get a molar mass of 159.609 grams per mole, or the same unit we know could be atomic mass units. So if you need help at this point in getting the molar mass, also let me know. I'm not going to show this explicitly here. So again, we're taking the mass of just copper, sulfur, 4 oxygen atoms, looking at the periodic table to then get this total molar mass of 159.609 grams per mole. So now that we have that, we can go into the last step here. So 0.1376 moles of solute, and we have this conversion factor to work with. If we want just grams at the end, then we should orient this such that 159.609 grams per mole. So when we orient it like that, we can cancel out moles and moles, be left with just grams. When we do that division, we should get now 21.96 grams of our solute. Then we need to check, is this in the right number of sig figs? Well, our initial volume only had 2 sig figs, so we should only have 2 sig figs in the end. So this will then round up to 22. And remember putting that decimal point here to note that this is 1 sig fig and 1 sig fig. 22 on its own also implies we have 2 sig figs. Remember, if it was 20 with that decimal point, this is 2 sig figs. But 20 without that decimal point, this implies just 1 sig fig. So just another little review on sig figs to keep in mind. So then we have our final answer here of 22 grams of our solute that are needed for this total volume of the solution. And there are some additional practice problems in the main slide deck on molarity. So be sure to check out 4.7 and 4.8. And also let me know if you have any questions or if you want to work through any of these together. So keep me posted. Now the next topic in chapter 4b we're going to go through is on dilution. So now we're taking 2 solutions and we're connecting them using this concentration equals N over V. So essentially we're going to use 2 different solutions where this describes one solution. Then the concentration of a second solution is really N2 over V2. So now we're going to use these 2 equations and connect them for this whole topic on dilution. So to define dilution, it's the process, it's the procedure for preparing a less concentrated solution from a more concentrated solution. So we're taking a more concentrated solution like we see in part A, then we're diluting it into this less concentrated solution. So more concentrated than less concentrated. I want you to notice something right away about the number of red spheres in the more concentrated. This is more concentrated. This is less concentrated. So it's more concentrated because we have more of these particles in less amount of total volume. Then you'll notice in B, we still have the same amount of particles. So really importantly, same amount of solute. For a dilution like this, where we're just adding solvent, we're just adding volume, we still have the same amount of solute, particles. But then we've added more volume. So again, this is more concentrated, so less volume. Then less concentrated because there's more volume, for all of these spheres to spread out through. So this whole principle that we're seeing comes back to this other really important idea of dilution, where the moles of solute before dilution is the same as the moles of solute after dilution. Okay, so going back up here, so the moles of solutes is the same before and after dilution. So this could be our before, this could be our after dilution. So if these terms are the same, then we can make this really handy dilution equation. So let me show you this. So N1 is equal to C1V1, just rearranging this one. Then N2 is equal to C2V2, just rearranging this equation. Now, if the number of moles before the dilution is equal to the number of moles after dilution, then N1 is equal to N2. With this equality, that makes C1V1 equal to C2V2, where these ones denote the solution before dilution, and these twos note the concentration and volume after dilution. Okay, so C1V1 equals C2V2 because the number of moles before and after dilution are the same. So now let's go into this practice problem and use these dilution equations, or use this dilution equation and in practice. So let's go here. So here we're told a chemist makes this amount of milliliters of barium chloride working solution by adding distilled water to 210 mils of this molar concentration stock solution. So importantly, it's really crucial to label all of these correctly. So if one is going to denote before dilution, so let me write it down here bigger. So C1V1 is going to equal C2V2, where the ones are going to denote before dilution. So if these are denoting before dilution, another way to think about them is that these are denoting the stock solution. Okay, so stock solution, then the diluted solution, we can call it diluted or after dilution. So for a stock solution here, if we have some solution we made in the lab and it's some concentrated stock solution, if we're going to dilute that into another volume vessel, then we're taking some stock solution and we're diluting it. Okay, so a stock solution is some given concentration, and we're going to call this before dilution. Here's our stock solution before dilution, and here's our diluted solution after dilution. Okay, let's start figuring out what these different variables are and what we have in the given problem. Let's start here. So this is saying by adding distilled water to 210 milliliters of a 0.386 molar stock solution. So we can label now that the concentration before dilution, or of our stock solution, is 0.386 molar. Then our volume here of our stock solution, or before dilution, is 210 milliliters. Okay, so now we dealt with this value and this value. Now here in the rest of the problem, we're told a chemist makes 610 mils of this other solution. So at the end, they made this new solution. So this is really our volume 2. So they made some new solution that has this specified volume of 610 milliliters. Then we're asked to calculate the concentration of the chemist's working solution. Okay, so diluted solution after dilution. In this case, we're calling it our working solution. So we go from a stock solution to a working solution, and we'll solve for this. Let me give you some additional background on this sort of formula. So as mentioned, we can write out C1V1 is equal to C2V2. Another way you might see this denoted as before and after dilution. Remember, we called this our before and this our after. You'll see this denoted in a few various ways. So some people use C1V1 equals C2V2. Then in ALEKS, it's shown as N naught, C naught, and V naught. And then after dilution is just N, C, and V. So essentially here we're saying C naught and V naught. Then for the after, we're just told it's C and V. So whatever form of the equation works for you. I'll show you even a different way we can represent C1 and V1 and C2 and V2. So this is saying what I showed here, where the number of moles is equal before and after dilution. So we can end up equating these to get this sort of formula. This came from this visual here, where the number of moles of the stock solution does not change when it gets diluted. So number of moles is the same. So now coming back here, this is where we're equating N naught and N, or our N1 and N2. When we equate these, then we can get this similar, very similar equation to the C1V1 equals C2V2. So this is basically the same thing. It's just slightly different notation. So C1, V1 is C naught and V naught, equal to C2, V2 is just concentration and volume of our solution after dilution. Okay, so now we're going to use this one like we were starting to set up on the last slide. And I'll show you even some more variations of this equation, or of this set of equations. To refresh you, as we're going to call it now, V naught is the volume of the solution, C naught concentration, N naught moles, and these all refer to the before dilution values, the initial or pre-dilution values. Then here, for after dilution, or our working solution, we can have volume, again, concentration, and number of moles. Using this connection that C naught V naught is equal to CV, right? Same thing as C1 V1 equals C2 V2. We can then solve for different variations. So here we're solving for C. We can also solve for C naught if that's our only unknown. So for solving for C, that means we're solving for this concentration after dilution. If we're solving for C naught, we're solving for the concentration before the dilution. And so what we're doing to get these equations is we're rearranging this base equation for dilution. So C naught, V naught equals CV, dividing both sides by V naught, that leaves C naught as CV over V naught. Then the way this is represented is like this. So we can actually say C times V over V naught. So these are all the same thing. It's just rearranging this equation and then pulling the C out front to take the volume over V naught. So now rearranging this equation, if our volume is unknown, we can also solve for the volume here after dilution. We can solve for the volume here before dilution. Okay, so all these different variations of this same base dilution equation. To reiterate again, it's really important to remember that the moles of solute does not change in these dilution problems. That's why we could equate N naught and N. So this is a really important factor moving forward in these dilution problems. The amount of solute does not change before and after dilution. Then in solving our practice problem, we're going to use the concentration and volume of the stock solution we were given, as well as the total moles of barium chloride present and the volume of the working solution. So let's go through and start solving our practice problem now. So here's our equations up here. C1V1 equals C2V2, or if you prefer, C naught V naught equals CV. Coming back up here, we do have the concentration before dilution. We have the volume before dilution. We also have the volume after dilution. So there's a few different ways you can solve for this. Let's go through this method. So step one, we're going to find the moles of barium chloride present before the dilution. Okay, so everything now that we're labeling either C1 and V1 or C naught and V naught. So everything before dilution, which in this case we're referring to our stock solution. So our stock solution here, we know the molarity is 0.386, writing this out as moles per liter, and the volume we were given is 210 milliliters. So now just focusing on concentration equals number of moles over volume of our stock solution. So I'll call it C naught here to be consistent. So we have concentration, we have volume, we can solve for N naught. So this is C naught times V naught. We can solve for, here this would be the moles in our stock solution. So now let's plug in concentration here. So 0.386 moles per liter. This volume is currently in milliliters. So let's first convert this out of milliliters by taking 210 milliliters. There are 1,000, one extra zero there. There are 1,000 milliliters in 1 liter. Milliliters cancels out. We have 210 divided by 1,000. That comes out to, moving this over 1, 2, 3, about 0.210 liters. Now we can multiply this by 0.210 liters. Liters and liters cancels out. Then we have our number of moles to be about 0.081060 moles. This is the number of moles in our stock solution. So if we have the number of moles in our stock solution, and the number of moles will be the same in our stock solution and our diluted solution. So now we have the number of moles for our diluted solution as well. We also have this volume here, and ultimately we're getting closer now because we just want to calculate the concentration of this solution, and now we have the number of moles and we have this volume. So you have this many moles, we have our volume is 610 milliliters. If we want to report this as a molarity, we need to convert this into milliliters. So now we're going to take 610 milliliters. There are again 1,000 milliliters in 1 liter. Mils and mils cancels out. 610 divided by 1,000, moving that over 3 times, 0.610 liters. All right. So now we have number of moles and volume of our working solution or our post-dilution solution. So now from this formula here, N over V, we have a value for N and a value for V. So now we can plug these in. So 0.081060 moles per 0.610 liters. So now we are going to get a molarity as our concentration. This comes out to 0.13289 moles per liter, which then we can rewrite as 1.3289 molar, right? So moles per liter is our definition of molarity. So moles per liter here, we did calculate a concentration in molarity. To get this into just 3 sig figs total, this is 0.133 molarity. So that's our concentration of our working solution now in 3 sig figs in the units of molarity. So what we did to solve this problem successfully is again using that key fact that the moles will not change upon dilution. So the moles does not change upon dilution. So N naught and N are going to be the same. So number of moles before dilution, number of moles after dilution. Then we can equate these two to then get this general formula for a dilution equation. Then we covered these as well. So some different variations. Here's our main dilution equation. We can also just solve for concentration after dilution by rearranging this. We can also just solve for volume after dilution by rearranging it this way. Then yet another few variations is to solve for the volume before the dilution as well as the concentration before the dilution. So all these different variations just again come from this main equation of C1V1 equals C2V2. or if you prefer, C naught V naught equals CV. So these are all the same thing, and then we can rearrange this to then solve for concentration and volume before dilution and concentration or volume after dilution. This is the final answer we got in 3 sig figs, right? So 0.133 molar. There are additional practice problems as well in the main slide deck. So on molarity. Molarity, again, is a really important concept in chapter 4. Before we go on to the next topic, I'm going to introduce yet another way of noting the C1V1 equals C2V2 or C0 V0 equals CV. So what I prefer to use is actually M1 V1 equals M2 V2. The reason that these are M's and not concentrations is because these stand for molarity. So these stand for molarity specifically here. So M1V1 equals M2V2. You might hear all these different variations of our dilution equations. So in the way we solved this, we went ahead and solved for the number of moles here, then we divided by the total volume. There's another way you can solve for this concentration in one step. So we can rearrange this equation as we've been seeing, right? So C2 really equals dividing both sides by V over 2. So C1 V1 equals C2 V2. So now to rearrange to solve for just C2, we could divide both sides by V2, leading to C2 is equal to C1 V1 over V2. Okay, so we can also solve for it that way. So I just want to show you this really quickly. So now we could take C2 here is equal to 0.386 moles per liter or molarity times 210 mils divided by 610 milliliters. What's nice about this way is we actually don't have to convert any units because milliliters and milliliters cancels out, leaving C2 in the units of moles per liter. So as long as this volume unit is equivalent to this volume unit, then you actually don't need to do the conversion because those units will cancel out. So you could solve for concentration 2 or the concentration of the working solution by taking, again, C1 times V1 divided by V2. So that's one way we can do it all in one step. So we would get the same answer doing it this way as well. So next we have solving for a reactant in solution. So before getting more into this topic, let me introduce you to this concept of gravimetric analysis. So in gravimetric analysis, we can dissolve an unknown substance in water. So say we took some solid substance, we dissolved it in water. We can react that unknown substance that's now dissolved in solution, react it with an unknown, react the unknown with a known substance that will form a precipitate. So then that precipitate will form, remember it's sort of a solid or a semi-solid denoted like this. So a precipitate forms, we can filter and dry that solid precipitate, weigh that precipitate, then use the chemical formula and mass of the precipitate to determine the amount of an unknown ion. So this is how we could do gravimetric analysis in the lab or in a virtual lab. So taking an unknown, then adding some known substance that will form a precipitate with that unknown. Then we can identify the specific ions that went into forming that solid precipitate. If the unknown, if we have no idea what it is, it could take some trial and error to figure out the right known to add that would actually form a precipitate. But this is just a concept of gravimetric analysis. So let's try this practice problem. Let's say we have metal copper is produced by dissolving a mineral which contains copper 2 carbonate in a concentrated sulfuric acid solution. The sulfuric acid reacts in a concentrated amount of sulfuric acid. So then the sulfuric acid reacts with copper 2 carbonate to produce a blue solution of copper 2 sulfate. So fun fact, solutions with copper 2 plus usually appear blue, depending on what else is present in solution. So copper 2 plus will form this blue solution. So then we have scrap iron is added to the solution. So iron is added and pure copper metal precipitates. So here is our pure copper metal. We know it's pure copper metal because it's just copper listed here as the element, and then solid metal here. So copper in its solid form is copper metal. Then suppose this quality control chemist analyzes the sample, then he adds some known to it, so iron to 450 mils of copper 2 sulfate. So as you can see, we're kind of getting at this gravimetric analysis method. So we're adding some known to it until no more copper will precipitate. Then he washes, dries, and weighs the precipitate, finds it has this specific mass. Okay, so we had some idea what's in solution. Now we're going to perform gravimetric analysis to then, for our final answer, we want to calculate the original concentration of copper 2 sulfate in this sample. Based on this balanced reaction, we do have to make sure it's balanced, looks balanced. So based on this reaction and based on how much we're getting out at the end of this final mass. So we're asked to calculate the amount of copper 2 sulfate that was in the original sample. It was consumed by the precipitation reaction to form a solid, which was then washed and dried and weighed. So from the amount of pure copper that is produced. So some amount of pure copper is produced, but we want to find out information about the copper 2 sulfate. So because we have a balanced reaction and we're connecting one reactant to one product, this should make you start to think that we're doing a stoichiometry style problem. So the key to all stoichiometry style problems is absolutely to have a balanced chemical equation. As you'll recall, for balanced chemical equations, these tell us the moles of all the reactants and how they relate to the moles of all the products. So just really importantly, for stoichiometry, remember when in doubt, convert to moles. So these molar coefficients here, they're actually all just related by 1 mole to 1 mole to 1 mole to 1. So remember these though tell us the mole to mole ratios of our reactants and our products. But in our problem, we're not given directly the moles of copper, or are we asked for the moles of copper sulfate. Instead, we have a mass of the copper precipitate, right? So we have this mass of the copper precipitate. Then with this mass, the copper precipitate, we're asked for the concentration of copper 2 sulfate in this original sample. So now with all this different information, it means we'll have to do some mass to mole conversions and also some mass to volume to concentration conversions. So let's start to get organized and then solve this problem. Coming back to get organized here, the mass of the precipitate. So here we're told the mass of the solid precipitate, which means this is the mass of just pure copper metal. So here our precipitate, we know we can recognize a precipitate with that solid here in a balanced chemical reaction. So our solid precipitate here is pure copper. So pure copper metal, we have the mass of pure copper metal. Remember, when in doubt, we want to convert to moles. Okay, so we have a mass of pure copper metal, and let's convert to moles. So 117 milligrams of pure copper metal. Looking at the periodic table for our molar mass of copper, then we have copper here weighs 63.546. This is, remember, in units of grams per mole. So now using that molar mass, or better named atomic mass, because we're just dealing with one atom here. So not molecular mass, it's not a whole molecule, just one atom of copper. So one atom of copper weighs 63.546 grams per mole. We wanted to put mass in the denominator so we could cancel out grams and grams, but oh wait, we also need to deal with the fact that this is now in milligrams. So within the same step, let's actually convert milligrams to grams. So we're going to leave this as is. Then for every 1,000 milligrams, there's 1 gram. So now to cancel out what we have, milligrams and milligrams, grams and grams, all of copper, leaving just moles of copper here after we do this multiplication and division. So that comes out to 0.0018411 moles of pure copper metal, or copper precipitate. So it's important to label this here because we're going to connect moles of copper precipitate to moles of copper 2 sulfate. So let's label that very clearly now. We're going to keep this number of sig figs and then go into our next step. So we have this many moles of copper precipitated, 0.0018411 moles of copper precipitate. So we have this amount here. We want to connect this to the moles of copper to sulfate. So the mole to mole ratio here with these coefficients is 1:1. So moles of copper solid is the same as the moles of copper 2 sulfate. But it's not always going to be that straightforward. So let me show you how you would set this up, even if it were 1:1 or 2:1 or 2:3. So again, these molar coefficients are not always 1:1. So we could say for every 1 mole of copper solid, right? So here connects for every 1 mole of CuSO4 aqueous. And importantly, we want to put copper solid on the bottom here in the denominator, then labeling all of this very clearly. This all cancels out, so then we have moles of copper 2 sulfate here because we kept this in the numerator. So that really is just multiplying this value by 1, but I wanted to show you this process in case the molar coefficients aren't 1:1, and usually they're not 1:1. So this would come out to the same number, but then moles of copper 2 sulfate aqueous. Okay, so yes, same number of moles based on this, very, very importantly, based on this balanced chemical reaction. If it were not balanced, we would need to balance this first, absolutely, to get these correct molar coefficients here. In this balanced reaction, they are all just 1:1:1:1. So now from moles of copper 2 sulfate, let's go back to our original problem here. So we want to calculate the original concentration of copper 2 sulfate. Now we have the moles of copper 2 sulfate. We also have a little bit more information here on this volume. So this chemist added powdered iron to 450 mils of this copper 2 sulfate sample. So this itself is 450 mils. We also have the number of moles. So let's finish connecting the dots and get ultimately what we're asked for, which is the concentration of copper 2 sulfate. So one piece of unused information so far in the problem is this many mils of copper 2 sulfate. Then from this slide, we did figure out that we have this many moles of copper 2 sulfate. So 0.0018411 moles of copper 2 sulfate. To be fair in this question, they should specify calculate the original concentration in grams per milliliter or grams per liter. Because if you read this as calculate the original concentration, it could be somewhat arbitrary. Are we calculating moles per liter? So here we're calculating concentration, but in grams per some volume. So because we have moles, we do need to convert into grams, then divide by this volume here to ultimately get our answer. So we have this many moles, but we want to convert into grams. So to do that, we're going to multiply all of this by the molar mass of copper 2 sulfate. Again, if you have any questions on how to get the molar mass from the mass of copper, sulfur, and 4 oxygens, remember you go to the periodic table, look up the mass for copper, and now sulfur, and now oxygen. The oxygen you'd have to multiply by 4, so this 16 times 4, because there are 4 oxygens here in this ionic compound formula, or in this formula unit for copper 2 sulfate. So now we need to put grams in the numerator because we want to cancel out moles and moles. So 159.609 grams of copper 2 sulfate. We're going to keep being really specific, grams of copper 2 sulfate, so labeling what this is per 1 mole of copper 2 sulfate. So now at this point, moles cancels out, leaving just grams of copper 2 sulfate. So that is 0.29385 grams of copper 2 sulfate. And again, we want the concentration in grams per some volume. So that's why we need to first convert moles into grams. If we were asked for a molarity, we could have kept this in moles, right? Because molarity is moles per liter. Here, though, we're asked for a concentration in grams per volume. So now we have grams. Then the last step is to divide it by the total volume. So here we have 0.29385 grams of copper 2 sulfate divided by 450 milliliters. That comes out to 6.5300 times 10 to the negative 4th grams per mil. We're not quite done because we actually want our final answer in grams per liter. So 6.5300 times 10 to the negative 4th grams per mil. Then to convert milliliters into liters, we say 1,000 milliliters in 1 liter. Then milliliters and milliliters cancel out, leaving grams per liter. So taking this amount times 1,000. So if this is times 10 to the negative 1, 2, 3, 4, this is really 0.001230653. Then we're multiplying by 1,000, so that's really moving this decimal point back 1, 2, 3. So if we didn't have a calculator, we could start to reason through this, but you can also definitely use your calculator. This comes out to 0.6530 grams per liter. We only want 3 sig figs though, so then we end up not including this 0 here. So then our final concentration, or I should say our initial concentration of copper 2 sulfate, the final answer for that is 0.653 grams per liter. So here we have 0.653 grams per liter. Pay attention to what units of concentration you're being asked to calculate, because here we wanted grams per liter. You may also want to calculate at some point milligrams per liter or moles per liter. Here you would be asked for the molarity. So just pay attention to what units you're being asked to calculate. This is a version of the periodic table that is available for you on Canvas, so this is always accessible. Let's do another type of practice problem based on molarity, but now also with this inclusion of a concept of the percent by mass. So we went over this initially, I think in chapter 3. Now we're going to connect percent by mass. It could have been earlier in chapter 4. Now we're going to connect percent by mass into a gravimetric analysis kind of problem, because we have this unknown metal, we have this ionic compound, and we're also told we have this many grams of this precipitate that forms. So now let's solve this style problem that's slightly different and adds in this layer of complexity by including this concept of percent by mass. So to remind you on percent by mass of Cl specifically. So this could be percent by mass of oxygen, hydrogen, carbon, essentially any atom. But here we're asked for percent by mass of Cl. So percent by mass of Cl is going to be the mass of Cl in grams over the mass of the whole compound, right? So percent by mass of something in relation to the mass of the entire compound. To get it into percent, then we'll multiply by 100%. In setting this up, let's definitely label everything that we know first. So this is 0.5662 grams of ionic compound that is unknown. It does contain chloride ions. We can write out Cl minus ions. It does contain Cl minus ions. Then we know that an unknown metal is dissolved in water. So some metal is dissolved in water, leading to, well, with an excess of AgNO3. So if you remember the limiting reactant idea, because this is in excess, this is saying that whatever is in excess then is not the limiting reactant, right? So it's not the limiting reactant if it's in excess. We're told from all of this that we get this much, 1.0882 grams of AgCl precipitate. So let's write this out as AgCl solid. Okay, so we had an ionic compound contained Cl, a metal was added with water with excess silver nitrate to form this many grams of a solid precipitate. And we want to know the percent by mass of Cl in this original ionic compound. Well, what we know is this formula for percent by mass. We also know this total amount of the compound that contained chloride ions. So now one connection we can make in solving for percent by mass is we have the total mass of the sample, but we don't know the mass of just Cl minus. So we don't know the mass of just these chloride anions or chlorine in the sample. So we need to solve for this, then we can solve for percent by mass. To solve for this Cl minus amount, we need to think about what sources of Cl minus there are in our setup of our problem. So the only source of Cl minus ions is in that original compound, right? So it's in this original compound. These chloride ions eventually end up precipitating and forming AgCl solid. So back here we have our ionic compound with metal and water. So really here's our ionic compound that's in the solution as well. So our unknown ionic compound. Then this forms this mass of AgCl, and we're not really concerned with the silver nitrate because that's in excess. So all of the Cl minus from this original compound goes into forming this many grams of this solid. So at this point, we do know the mass of the sample, the original sample that contained Cl minus. We don't know the mass of Cl, but then we also do have this connection between the Cl from our unknown into forming this total precipitate or silver chloride. Well, what this gets at is that any ratio of Cl into AgCl can be described by their molar masses. So without even worrying about the total masses we're given here, we just know that our Cl from our unknown goes into form AgCl. So now just focusing on the percent Cl in AgCl. So one Cl atom weighs 35.45 grams. Then overall the molar mass of AgCl is 143.4 grams. So chlorine, a halogen, 35.453 grams per mole. Then Ag with Cl, here's silver, 107.868. So AgCl altogether is this mass plus this mass. By taking the molar mass of just Cl over the total mass of AgCl. So that means within silver chloride, 24.72% of that is going to be our Cl minus. Okay, so that was an important connection we needed to make here. So percent Cl just in a general compound of AgCl is 24.72% chlorine in any compound of AgCl. So it's 24.72% by mass. We know it's percent by mass because we had grams and grams here. So now in any compound of AgCl, 24.72% of it is going to be composed of Cl specifically. Then the other percentage of that is going to be composed of silver. right? So if we took 100% minus 24.72%, then about 75% is just the mass of silver within silver chloride. Okay, so 24.72% by mass of Cl within silver chloride. Now to further connect this, we were told that altogether silver chloride precipitate formed and it weighs this much. That means that out of this many total grams, 24.72% of this mass is going to be composed of Cl, or attributed by Cl. Then the other portion of that mass, of course, has to come from the silver. So we need to find 24.72% of this total mass. So if we divide this by 100 to get it out of a percentage, so 1, 2, that's equal to 0.2472. So in finding 24.72% of the total mass of silver chloride, we want to take 0.2472 times this total mass. That tells us in the final precipitate, there's this many grams attributed by Cl. Then with this much attributed by Cl, that had to come from the original compound. So now this is the mass of Cl. This was the mass of the total unknown original sample. So with this mass of Cl, we can then plug that in here. Importantly though, because all of the Cl from the original unknown went into forming this silver chloride precipitate. So no Cl was lost to any other products. All the Cl went into forming AgCl. This was also based on this notion that silver nitrate, we were told, was added in excess. So this ionic compound, or unknown, was essentially our limiting reactant. So all of this would run out first before any of this did, meaning that all of the Cl here had to come from this original ionic compound running out. So all the Cl went into forming this. So then for our final last connection, we can say this many grams of Cl over the total mass of the compound, then multiplied by 100. I'm just going back, so 0.2690 came from here. Then the total mass of our unknown, 0.5662. So we plug those in here to then find our ultimately percent by mass of our original unknown ionic compound. So here is percent by mass of Cl, grams divided by grams, multiplied by 100%. Then we get this final answer here of 47.51% by mass of Cl in our original unknown ionic compound. To make sense of this value, we could check ourselves and know that AgCl is about 25% chloride by mass, right? Because we got it to be this 24.72%, or this amount here. So because 25% by mass of AgCl is our chloride, then roughly 1 gram of AgCl precipitate would be composed of about 0.25 grams. This 0.25 grams is a little less than half of this total sample of our unknown, our original sample. So therefore, about half makes sense for our final answer here. And that roughly 1 grams came from this amount here that we're told formed of AgCl. So that's one check we could do just to verify for ourselves. I'm going to go through the rest of 4B in the next part. Again, if you have any questions at all, please let me know. Molarity is a really important concept in Chapter 4, so hopefully you're getting comfortable doing practice problems. I hope you're all doing super well, and I'll talk to you soon.